Hello friends, welcome to my YouTube channel Mech Maharashtra, which provides you the educational videos. Next part will going to discuss about the centrifugal tension. Now basically we just find out what is the centrifugal tension coming over the belt. Now see the structure. In this structure what happened, the diagram, the belt is situated over a pulley, and while it is moving as per the rotation of the shaft, it will create a centrifugal force around the pulley. Now that force is indicated here. Now see here, the distance P and Q, you can see the distance P and Q, it is the actual arc of contact and through which the belt is going to move or move forward on tight side as well as a slack side with respect to d theta. Clear? Fc is nothing but the centrifugal force. As we know, the centrifugal means what? Away from the center. Force is acting away from the center. So that this will be the centrifugal force. Now these are the TCs. TCs means centrifugal tensions acting tangentially with respect to point P and Q. Correct? So this will be the points in the structure. Now we are going to find out what will be the centrifugal tensions coming on the belt. M is the mass of the belt per unit length in kg, which is moving around the pulley. Then V is the linear velocity of the belt. Correct? R is the radius of the pulley. Tc is the centrifugal tension at point P and Q. Now we can calculate the length of PQ. This very simple. Length of PQ is equal to R. This will be the radius of the pulley, R into d theta. So I have mentioned here R into d theta, and by adding the mass of the pulley, I'll get the mass of the PQ is mr d theta. Mass into radius into theta. That will be the angle between the point P and Q. Therefore, centrifugal force acting at a point PQ is Fc, centrifugal force, is equal to mr d theta, that is mass of the pulley, into velocity with respect to radius, that is v square by r. So here we have considered both the velocity tension on tight side and slack side. Of course that we need to consider because it is leaving from point P and Q. That's why v square by r. So generally centrifugal tension, the centrifugal force we calculate mv square by r. Am I correct? So same we will have to perform the mass we have considered mr d theta into v square by r. Correct? So by which, by converting this in simplified format, I'll get m d theta v square. Correct? R get cancel, m d theta v square. This will be your equation 1 for the finding out the centrifugal force. Now second, to finding out the centrifugal tension, that is Tc, these points, that Tc is equal to, you can see by comparing the centrifugal force with the tensions, I can say d theta by 2 is angle made at the top side and d theta by 2 angle made at bottom side. So I'll just take the tension of it, that is Tc sine of d theta by 2 upper side plus at lower side Tc sine d theta by 2, which is equal to centrifugal force, and centrifugal force we have already calculated m d theta v square. Clear? Then as d theta by 2 is very small, so we'll have to consider that directly as a d theta by 2 because d theta is very small. Therefore your answer would be Tc is 2 times 1 and 2, 2 Tc d theta by 2. We have considered as it is because it is very small, is equal to m d theta v square, this value. So therefore by cancelling this, we'll get the Tc is equal to mv square. Very important, very important. This will be our centrifugal force, and that can be always calculate this Tc is equal to mv, mass into velocity square. So this will be the relation derivation for the calculating centrifugal tension. By using centrifugal tension, we are going to calculate two more equations with respect to tension on tight side as well as slack side. You can see total tension, here they have mentioned TT1, no problem, we can say capital T. Total tension is equal to T1, that is tension on tight side plus centrifugal tension. This will be the relation we can develop. Or for slack side also, T2 is equal to T2, tension on slack side plus TC. Here T2 is not equal, T, capital T, that is total tension is equal to T2, tension on slack side plus centrifugal tension. So this will be the relation we have derived from the diagram for centrifugal tension. Now this relation also we can write down by this way also. You can see, as I told you many times, what happened, total tension they have considered TT, T of TT, so and TFT, tension on tight side, TFS, tension on slack side, same equation, correct, which we have seen in previous slide. Also centrifugal tension also compare with the initial tension. What is the initial tension, I will tell you in coming sessions, but just remember this, that TC is also equal to initial tension, that is 1/3 of initial tension. This will be the equation. And velocity of belt VB, correct. So VB is also equal to square root of total tension. Total means what, it is equal to T1 plus TC or T2 plus TC, likewise depends on tension on tight and slack side. Generally 99% tension on tight side will have to consider capital T, correct, divided by 3 times mass. So this will be the conditions for the belt velocity. So I hope you understood this session. I'll revise the session. In this session we have seen the derivation for the centrifugal tension, we have seen the diagram description, and then we move towards the calculating centrifugal force, this m d theta v square. Then we move toward the calculating centrifugal tension, and we have just compared these two, and by comparing we'll get the TC value, that is TC is equal to mv square, and with respect to total tension I'll get T1 plus TC as well as T2 plus TC. Same equation we have put here for understanding, because notations might be changed, so we don't confuse by that way, so we must know it. Then TC is also 1/3 of initial tension, and VB, belt velocity, is square root of T by 3m mass. Clear? So here I think you understood the centrifugal tension. So most of time they will ask the derivation. Okay, we'll see remaining part in coming lectures. Thank you.